Most cases it was.
Can online people hear now?
Last time it was early. Okay, excellent.
Yes, it works. Good. So that was a mandatory technical hurdle, right? I mean, you cannot have a hybrid talk without a technical hurdle. Yeah. Anyway, so as I was saying, like, so probably if you're an expert on Fractons already, you should just put your headphones on or whatever, and like can do work in the corner. So, but I suppose this talk could be useful for someone who is beginning in this new field of Fractons more recently, and might actually benefit from like an amateur's view on some of these rather complicated systems. So, okay, that disclaimer out of the way, I just have to figure out if this is gonna work. It does work. All right. Okay, wait. No, it does not work.
So it moves on your page.
Yeah, it moves on my place.
Did you mirror your screen or whatever?
I mean,
the usual thing with Macs that's.
No,
I mean, like, but I'm
see
connected
this thing,
by.
or you see the right thing, you never saw that you see the first slide and then the
Nice. So wait, wait. If you do this, can you go to your first slide? This is your first slide.
Yeah.
No, that's not the way.
No, I mean, this is probably going to work for the computer now. Okay, anyway, I think we are probably having trouble because it's full screen.
Go back.
I'm probably just gonna set it like that. You can see the title of my PDF, but I think at least it should work. No, it does not.
And if you don't go page, doesn't change.
Okay, let me. No. Yeah, it works now. Cool. Hurdle number 2 out of the way.
Sorry, one serious question. What is the feature of the fractals?
Oh, what does it have to do with fractals? To be honest, not a lot. These are actually has to do with fractals, which historically got stuck because it's like kind of rocky, I'm told, which has a kind of fractal structure. Now, the fractals I'm going to talk today has nothing to do with fractals, but it turns out the original fractal model, which was proposed in 2011 by Ha and some collaborators, that system had a fractal structure in the operators. So that's why these particles historically are called fractons. It's actually feels weird to call something historically when it was like 10 years ago, but yeah.
It's a very cunning picture anyway.
Yeah, but it's a nice picture. So like you invite people to fractons by showing them fractals. But that's all the connection that I'm going to have with fractals, at least in today's talk. Okay, so the big picture here is take any system, like specifically I mean a lattice system with a bunch of spins on the system. So, or you can just imagine any lattice with some degrees of freedom which are pinned to some sites on the lattice, and you have some local interactions. Now, typically, you would expect that if you take the system with these local interactions and these degrees of freedom, and you go to some IR limit, which is that you coarse grained over the system and went to some continuum limit in the deep IR, then you would expect that to have an emergent quantum field theory. This is pretty much, I'm not really a hardcore condensed matter theorist myself, but this is what I have been told for quite some time, that you can describe a lot of these condensed matter systems using field theory. And this is what the idea is. Like, you probably don't care about the UV degrees of freedom. You probably don't care about the macroscopic details of the crystal or of this lattice and these degrees of freedom. But in the IR, in the macroscopic description, there will be typically an emergent field theoretic description. Now, what I really mean by a field theoretic description in that sense is that there will be some local excitations in these systems, which you can think of as quasi-particle excitations. And once they're formed, these quasi-particle excitations will have some topologically conserved charges, and then they can move around in space. And you can just write down an effective field theory for these quasi-particle excitations and forget all the details about the microscopic theory where we came from. So this is a big picture, and it works all nice and fine until recently, as I said, around 2011. And so people started to actually find some lattice models that do not have this nice property. So I think, to me, one of the most striking features of these models are precisely that there are these local excitations. It is debatable whether you want to call them quasi-particle or not, but these are local excitations which somehow cannot really move. So the extreme case is what are called fractons. So these are quasi-particle excitations that once created will be pinned to a lattice site. They cannot really move in space. Then there are generalizations. There are lineons which can only move in a line or like a string inside your system. Then there will be planons which can move in a in one-dimensional surface. And of course, these are the only kinds that you can have if you are in 3D. But you can imagine if you go to higher dimensions, then there will be more of these kind of particles. Yeah.
Are there experimental realizations of such things?
That's a very good question, which I asked myself while preparing this talk as well. I think people are trying to realize these experimentally, but I think right now they appear, I think mostly in quantum correction codes and some phenomenological model for quantum glasses. So, but these are mostly theoretical. I think they have some applications in terms of qubits. So people are trying to, qubit storage in quantum computing. So people are trying to realize these systems experimentally, but I
see, but it's not that there's some material that you're interested in.
no. So yeah, so this is not the motivation here. I'm not trying to describe a material. Rather, I'm trying to basically poke at the assumptions of the field theory itself. So whether every lattice system with every kind of local interaction can admit a description. If it turns out useful for a physical system, it's nice. If it turns out useful for quantum computers, it's even better. Right? But no, I don't have any experimental setup in mind, unfortunately.
So why doesn't it work to just localize these excitations with the potentials?
So they are very strongly constrained in that. So if you want to localize them with potentials, you'll have to have delta function potentials. So they will. So in that sense, if you were expecting a smooth continuum field theory, then that's what you want. So that's what I mean here. Like if you have a smooth potential, then these particles can still move within a range. But here I'm really talking about these particles when they created, they can fundamentally not move.
So is there a problem in quantum field theory with delta function potential?
That is an answer I don't know, but I suppose because it's not smooth, some things. I don't know how useful it is, but I suppose at the end of the day, the description that people come up with turns out to be very similar. Yeah.
Does this thing have anything to do? Like I can imagine some curiosity with some sort of defect.
Yes.
And fields that are stuck on the defect. Is this how I should be thinking about this?
So if you think about, for instance, a field, a crystal or field theory with defects, typically, these defects are not topologically conserved. So in principle, they can move. So so for instance, they are like if you have impurities in a crystal, then this will make like point-like defects. But in principle, these things can move. So this here I'm talking about really quasi-particle excitation that cannot move. I'll go to a particular model, and then it should become a little more clear what are the kind of systems I'm talking about.
But there's still a link with the dynamics of defects, right?
Yes.
For instance, dislocations they can only.
Yeah, and so they are like dislocations in some particular setups.
Yeah.
Yeah. So it's like somehow your theory has symmetries that will basically prevent them from moving. Okay. So I'll come with a particular example in a bit. And of course, needless to say, we are still trying to understand how these systems work, whether or not they're useful, whether they're something trivial, is also up for question. So this is a system. So this is a concrete example I have in mind. It's the X-cube model, as it is typically called, proposed a couple of years ago by these nice people here. And so as I said, there are other Fracton models as well, but I'm going to mostly focus on this because this is a good toy model for me to start building theories. Okay, so just imagine like a cube, and on the cube there are these links, And on every link, there exists a spin. So what I mean by spin really is like there will be a set of Pauli operators. Take them to be x and z, sigma x, sigma z, and they have those commutation properties, and they square to 1. So it's like a Z2 system. And now, I mean, if it was a typical Ising model, I would have nearest neighbor interactions. So in the Ising model, I would write down 2 particle interactions between nearby links, if I will. And here, I have a little more exotic setup in mind. I have this 12 particle interaction. So every cube inside my on my lattice, inside every cube, there will be an interaction which corresponding to all the 12 links that make up that cube. So this is, I mean, you can argue whether this or not is a useful thing to do. I wouldn't question that. I'm just saying, okay, just take it to be a given that there is a crystal. I mean, there is a lattice on every lattice and on every link resides a spin, and then there's this 12 particle interaction. On top of it, I have another interaction. It's a 4-body interaction. So on every vertex, of course, every vertex connects to 6 links, but I will write 3 independent interactions where the spins are only coupled to spins that lie in a plane. So for instance, you can take this one. This is like the BZ operator, which couples spins that are lying in the XY plane on any vertex. And similarly for Y and similarly for X. Now, okay, you can go play around with this model. There's something really nice about this model is that this model is exactly solvable. And why is that? Is because every term in the Hamiltonian actually commutes with itself. Of course, these terms themselves commute because they are all just Z operators. They commute between different lattice sites because there are no, operators at different lattice sites commute. But more importantly, the A operator here and all the B operators there also commute. So you can just go write down this, do the little bit of algebra and you'll find the commute. So basically, if you want to minimize the Hamiltonian, for instance, you can minimize each of these terms independently and you don't really have any coupling between different Hamiltonian terms. So you can actually go back and try to really exactly solve this model. And that's what these guys do. They really motivated this model precisely because this was exactly solvable and it had some nice features. They went ahead and completely solved this theory and found out all the spectrum. And that's where they found these bizarre features that I'm going to talk about next, which we now call fractals. Yeah.
Once you add the B interactions in the X, Y, and Z,
yeah.
What's the residual symmetry?
So the residual symmetry, I'll just talk about it a bit. So these are called subsystem symmetries. It's just on my next. So this is like a smoking gun of fractonic systems. These precisely symmetries that I'm talking about.
You did not introduce coupling here, but I guess there is an independent coupling for
oh, yeah.
A and the B, right?
Yeah, so you can put independent couplings there if you want. So this, but yeah, I'm just going to set them to 1 just to avoid parameters splitting around. Okay, does work with the ladder. Okay, so there's some nice features about these models. I am not going to study this model in detail. There is a lot of discussion literature, also a lot of good talks on YouTube which study this system in detail. But I just want to pick out some salient features which will be important for me as I move along. So the first thing is that if you take this system and put some periodic boundary conditions in all the 3 directions, that is like putting it on a flat 3 torus, then the number of ground states that the system has scales with the system size. And actually, if you have a macroscopic system with quite large dimensions, then you will find that there are actually exponentially large number of ground states that the system can take. So this was a computation that was explicitly done again in this paper that I mentioned. But this is a bizarre feature because again, there are a lot of ground states for the system to choose from. So I don't know how we would handle the system, but I think it's a direct consequence. So as it turns out, it's a direct consequence of this question that you were asking, that there is a subsystem symmetry. So typically, if you take like a spin Ising model, it's invariant if you flip all the spins. Of course, because the Hamiltonian doesn't care if you were to flip all the spins at once. But the system has something even more. If you take any plane and you flip all the spins in that plane, It could be an X plane, Y plane, or Z plane, doesn't matter. But if you flip all the spins within a plane, then the Hamiltonian doesn't care. And it's actually quite easy to see. If you take a cube, then a cube makes up, comprises of 4 links which have been flipped. And of course, when the 4 links flip, at the end of the day, you will not get any correction. So there's that. There's that symmetry. And of course, in every link, you can again see, for instance, the link that corresponds to X and Y only has 2 of these spins flipped. So it again doesn't care. And the Z one has all 4 flipped. So it doesn't care again. So you can convince yourself that if you were to flip the spins in any plane, you will get the same system back. So, and now this is a very large symmetry, because if you have a very large system, then you can, in the continuum limit, you can imagine that you are flipping spins at every, in every plane possible in your system. So this is like really the smoking gun of these systems, these fractonic systems, is that they have a very large symmetry. And this is partly responsible for the large number of ground states, because if you can imagine, if you start with any given ground state, then you can apply these really large number of symmetry transformations to get a really large set of allowed ground states as well.
Same will be true for the vertical planes as well, right?
Yes, so this is true for horizontal, vertical, and all.
Yeah, we all did.
Yeah, so this is why the states scale with all the 3 dimensions independently.
So those are precisely the ground states. If you start from the configuration all spin up, and then you act with all possible.
Yes, so that's pretty exactly. So you start with a setup. So you first take into account the degeneracy of all spins being flipped. So you start with some number of ground states, and then you apply with the symmetry transformation, and you will get this host of ground states. And all of them are obviously allowed ground states with the same amount of energy, because this leaves the Hamiltonian. Okay. Yeah.
The logarithm grows like the length. Does this have some holographic interpretation, or is it interesting or not?
Yeah, I would like to know the answer to that question. I don't know. Okay, and for this talk, the feature that is most important to us is restricted mobility, as I'll just find out that these systems actually admit excitations that once produced cannot move. This is the first kind of excitation.
Sorry, although you are writing for 3 spatial dimensions, you can write down a similar equation for the ground state for any dimension, right? Cubes setting up in this cube form is difficult in higher dimensions.
Yeah, I think so, but you have to be careful with the number of dimensions. For instance, in 2 spatial dimensions, there will not be a subsystem symmetry. You can imagine there is a squares, and
but there will be lines, right?
Yeah, so whenever you flip lines, a square only only has one of the lines included. So that line term will flip. So you have to be in odd number of dimensions for this to work. But yeah, you can in principle do it in any number of dimensions. But yeah, you just have to make sure that the symmetry actually exists. Right, so these are the first kind of excitations. I'm going to be very schematic here because I don't want to really go into the detail of this particular lattice theory. But the idea is that if you turn at some lattice sites, you start with some ground state and you turn on some Z operators at some lattice sites. Of course, from this Hamiltonian, okay, you can kind of see that if you turn on the Z operators, then it will commute with all these 3 terms, and you will only be exciting the cube term. So because these 4 particle interactions are made out of Z themselves and Z commute, so you will only excite cube excitations, and that's what they look like. So if you take like a membrane, like a codimension to surface a square in your setup, and you turn on this bunch of Z operators, then as it turns out on the corner of this square, you excite these cube excitations. And okay, now once these excitations are created, they cannot really move, in the sense that if you want to, for instance, move this excitation here, you could do that or try to do that by introducing another Z operator, which will hopefully change the ground state. But of course, as soon as you operate with any of the Z operators, it turns on 4 excitations at the same time. So to try and move this excitation, you will end up getting 2 more excitations. So for instance, if you were to create a Z operator here, okay, now it works. So if you try to create an excitation here, it will annihilate this excitation, it will make it here, but it will also create 2 more excitations. So in that sense, whenever you try to move a fracton by itself, it tries to create more fractons. So basically, it tries to increase the energy of the system. So there is no way for a state or for a fracton to move itself without creating more fractons or without needing more energy. So in other words, there are no local operators that you can act around a fracton that will move the fracton. So this is what really people mean when they say fractonic excitations. On the other hand, you could imagine moving 2 fractons together. For instance, there is this operator and I take another copy of this operator and put it here. So it will again create 4 excitations. It will annihilate the 2 excitations here and it will create 2 excitations here. So essentially, you take any pair of these excitations, any pair which lies either horizontally or vertically, and you can apply this rectangular operator made out of z's, and this will move the 2 fractons. So in other words, fractons really cannot move themselves, but they can move in pairs. So they can move in dipoles. There's another type of excitation in these systems where you apply a bunch of X operators. So just like with the analogy with the previous case, if you excite a bunch of X operators, they will not excite the cube excitation because it itself is made out of X operators. It will excite the other 3 interactions. For instance, if you were to apply a bunch of X operators in X direction, then it will create 2 excitations at the end of this string operator. And these are called lineons because once you create such an excitation, for instance, consider this one here, the only way that this excitation can really move is applying another X operator here, which will move it to the next point. And similarly back and forth. But what it cannot do is it cannot move up or down. So if you take any such linear excitation and try to move it upwards by putting another X operator, it will actually leave some defected excitation here and then move upwards. So there is not really any way for this lineon to turn without needing more energy. So to turn, a lineon needs more energy. So if you don't have the supply of energy, then the lineon cannot move. So in other words, whenever a lineon tries to move, it decays into 2 independent lineons. Okay, so the lineons, as the name suggests, because they can only move in one direction. So you have 3 varieties of them, of course, in the system, depending on your dimensionality. And you can move accordingly.
So in the scaling limit, you're taking L finite?
So far, I have not taken any scaling limit.
Well, when you describe them as local excitations.
Yeah. So right now, when I say local, I really mean local on the on the lattice, as in I can define a region of subspace and a fractal is contained in it. But of course, I will go to the continuum limits soon, where I will keep the system size constant, but I will increase the number of sites and I'll decrease the lattice space in between.
And when you do that, you keep the length or the number of lattice sites fixed?
No, so
I mean between in your fractal excitation.
Oh, okay, but as I just said, it doesn't take any energy for this size to increase. So it doesn't really matter. So if you excite, if you take a pair of lineons and you push them apart, it doesn't take any energy to do that. So
how do you determine where they are? It's so confusing.
I think to do that, we'll have to turn on some external forces, which will act on these lineons. And that's like a gauge theory, which I will eventually come to, but right now it's a free theory. And of course, you create these excitations, but I'm not talking about measurements. Yeah. Okay. Then there are these composite excitations. So I already talked about 2 fractons. So you take 2 fractons, and then, for instance, in this configuration, then you can apply square operators to move it left, right, or in and outside the plane. You cannot move it upwards, because there is no square excitation that will move it upwards. So these are called planar excitations in the sense that these excitations are confined to a plane. So if you try to move them upwards, again, it will decay into multiple fractons. And if you don't have enough energy, then they're not going to move. Similarly, a rather slightly more complicated picture exists for lineons, and I mean, once you think about it, it's actually not so hard to figure out that if you take a pair of lineons and, for instance, this configuration, then this pair of lineons can again not move upwards, but it can move within. Okay, so this was almost the entire thing about lattice models that I'll need. So the thing I have in mind is that I want to describe a system, I want to describe a lattice system in continuum which allows for some excitations, some quasi-particle excitations that have some sort of restricted mobility. And a tool that comes out pretty handy and has emerged in recent literature is what is known as dipole symmetry. So, I mean, normally, if you have a quasi-particle system, you impose like a monopole symmetry. In other words, you demand that the number of particles are conserved. It's like a U1 monopole symmetry. But let's say that you also have a dipole symmetry, by which I mean that whenever an excitation is created, it can only move in a way so that its dipole moment is conserved. And if that is the case, then of course, if dipole is a conserved quantity, then from vacuum you can only create excitations in quadrupoles because you want the net dipole moment to be 0 before and after the excitation. And once you create these quadrupoles, any dipole subsystem of this quadrupole can move by itself, but but any individual excitations cannot move without violating the dipole symmetry. This is like an exotic symmetry. You can argue how physical or unphysical it is, but it gets the job done. So if you want to describe the continuum limit of these systems, this is the kind of symmetries you will typically encounter, is that there are these excitations and there is some moments that are conserved that are associated with these excitations.
Is this kind of, can be seen from the X-cube model?
So actually in the X-cube model, people have done explicit calculations where they properly integrated out and like did some dualization and realized the field theory. This was like work by Seiberg and company and also more recently. And there they actually find this emergent symmetry. So it's a little more precise than what I'm making it out to be. But yeah, this is like a motivation for you to consider, for instance, dipole symmetries. And as it turns out, the Fracton lattice models correspond to a state in the phase space in which this dipole symmetry is spontaneously broken. So this dipole symmetry is going to be a highly localized sort of symmetry. And again, whenever you explicitly break the symmetry, you create a bunch of ground states. And this would explain, for instance, why these systems have such large degeneration.
I mean, when you put it this way, that's really the same thing as what happens with vortices in the superfluid. You can create them as pairs of bound vortex and anti-vortex.
Yeah, but then a vortex can by itself move anywhere, right?
No. No, the pair will move because the winding number, the total winding number is conserved.
Yeah, but like,
as soon as you let one move on its own, then this will start relaxing the winding number.
I mean, winding number is.
And then you violate the conservation of winding number, which is an emergent symmetry of your superfluid.
Local winding number. Okay. Probably. I haven't. But I mean, okay, I haven't really thought about it.
I mean, this sounds really
okay. All right.
similar.
That's good to know. Okay, so now I'm going to start writing some equations and try to really get into it a little bit. So consider a field theory where there is some conserved U1 charge. So associated, there will be a Neutral current. I'm just denoting it like that. So there is a density and then there is a flux, and they satisfy a conservation equation. But what that really means is that if you would define a total charge density within any volume, then the time derivative of it is like, it does not evolve in time except flux is out at the boundary. This is like the usual Gauss's law kind of argument to say that the charge is conserved. So for instance, but I mean in the system, for instance, if you take any positive particle and you apply like a Gaussian surface around it, it will tell you that there is nowhere that this charge can decay by itself or can just go away. This charge, once created, is going to be conserved. In other words, whenever you excite vacuum, you will only always create charges in pairs, pluses and minuses. But once they're created, the plus particle and the minus particle or electron or positron are free to move anywhere in space. But what they cannot do is they cannot get into an interaction which will violate the charge conservation. But okay, this is the usual setup. But now allow me to do something a little fancy where I say that the flux is somehow a total divergence. So flux is a gradient. And then it's a little bit of exercise, but it's something you can do at the back of an envelope, is that you will find that if you define a dipole moment density, which is jt times xi, and then you integrate it over some volume and then you compute the time derivative, it again is conserved.
How should I understand that equation? So, I mean, before I thought we were talking about a density of dipoles, so there'll be some conserved number for dipoles. But this is something slightly different. It's not about you know, I'm thinking like dipole particles that make a cloud. This is you have some positive charge over here, some negative charge over here. They form some effective dipole.
Yeah.
And that's how I should think of this.
Yeah, so I mean, right now I want to think of this as, again, I mean, if you have a dipole, then you can presumably, if there's a dipole, there's an orientation, and you can, in your head, think about it as plus and minus particles.
Yes.
But then the effective description is really telling you is that, of course, the number of particles is conserved because number of dipoles is conserved, so it follows. But also individually, the dipole moment is conserved. So for instance, once you create a dipole, plus minus, you cannot rotate it. So this is like a vectorial conservation equation. So once a dipole is created from vacuum, you cannot rotate it. It can move about in space, but you cannot rotate it.
But I shouldn't think of your theory as consisting of a bunch of microscopic dipoles. These can be macroscopic objects with this equation.
Yeah.
So there's plus over here, there's minus.
Yeah, I mean, I suppose you can also go to that limit where you forget about individual charge excitations and only really think of the dipoles as the degrees of freedom.
Yes.
That's also possible, but right now I'm taking a slightly more simple approach. Okay, good. So of course, as we just said, once the dipole moment is conserved, yes.
Sorry, I was wondering about the symmetry of your GI theory.
Yeah.
What does it come from?
Oh, I mean, this is not coming from anywhere. I'm just putting it by hand for the moment. So I'm just saying that let's say that GI is given by total divergence, and let's say that the total divergence is, is symmetric. I mean, it just follows because if you put this guy here, then the entire symmetric part of GIJ drops out. So it doesn't really matter. So if I'm the only physical observable that I have control over is GI, then there's a redundancy to the definition of GI. So I define it so that it's symmetric. Okay, so as I said, the dipole moment is conserved. So once you create a particle, it cannot move because, of course, as soon as it starts to move, the value of x changes and the dipole moment changes. And of course, the charge of the particle cannot change because it's independently conserved. But, and same goes for the minus particle. But of course, when you create a pair of them, they can move because they have conserved dipole moment. There's another little bit of a more exotic object you can talk about. So as it turns out, because J is a flux, I mean J is a total divergence, then you can take the time derivative of J itself, and this will also be conserved. So which means that if you think about like a local current excitation, not sure how well that motivates it, but if you have like a local current excitation, then it can only move in one direction. I think in my head, I'm thinking about like, of course, if you have a bunch of positrons moving in a particular direction, then the dipole moment, then correspondingly, you will also have a bunch of electrons moving in the same direction so that the total dipole moment is conserved. And of course, you cannot change the direction or magnitude of any particular positron movement without also changing the electron movement.
So what is JI transverse?
Oh, JI transverse, this is just supposed to be because it's a surface integral. So so this is Jij, this object there, and then one of the transfers. So yeah, perp just means like the component transfers to the. So again, so if you think about a local wave packet which somehow has a flux associated with it, then again this particle can only move in one direction. So it's like a lineon. It cannot move in the other two directions because Gi is conserved. what is, so this is given by this expression here that J cross X. So the curl of J is 0. So J cross X is conserved as well. So once you start moving this linear excitation, this is itself it's conserved, so it cannot decay, but it cannot really move very much as well. In this setup, as I have already mentioned, you can create these dipoles. So these dipoles, once they're created, they are free to completely move. So this is slightly different from the X-cube model, because in X-cube model, we already discussed that dipoles cannot really move freely. They will only move in one direction. But yeah, this has some very simple, very similar salient features. As it turns out, if you want to further restrict the movement of these carries, you have to also impose conservation of higher moments. For instance, if you impose the conservation of quadrupole trace, just for instance, Jx squared, then the dipole will not be able to move in the direction of its dipole moment. So it's like an example, but I'm going to stay quite simple here and only consider carries with conserved dipole moment. So for now, my dipoles can move anywhere in space, so they're not really restricted to a plane. Okay, it's a little bit of group K. So the dipole symmetry algebra is given as follows. On the first two columns, I have the usual algebra. So again, you will see that I have a Hamiltonian for time translations. I have momenta, I have angular momenta. They have the usual commutation relations, and I have some charge which commutes with everything, just like the scalar U1 charge. I have intentionally dropped out any boost symmetry. And yes, question?
It's got a bit confused. So for example, if I were in a two-dimensional system, I understand you want to be in five dimensions.
Yeah.
Then I would also be having this sort of conservation laws because the current defining function set for multi-coordinate.
Sorry?
The current any function of the multi-coordinate.
Yes.
Is conserved.
Yeah.
Maybe I'm not allowed to have things that just grow as that. Can you comment something or like?
So yeah, I have not really thought about the conformal limit of these theories.
So maybe nothing applies because these are really in one spatial dimension and then.
Yeah, I understand like in two-dimensional conformal field theory, the symmetry group is very large. So maybe there are some subtlety associated with it, but of course you already avoid them in 3 dimensions. And plus, I'm not really talking about conformal models here. So of course, I have a very concrete lattice model in mind, so it's not scaling again. Okay, anyway.
What is D? D is
Oh, D, I'll come to D. D is the dipole moment operator. But so right now we just have the first 2 columns. I have the usual thing. I've intentionally avoided a boost. And this you can imagine why. For instance, if you have a ground, you have an excited state with some charged particle lying around. And then the boosted state, where this charged particle is moving with some velocity, is not an alarm state. So of course, so boost is not a symmetry of my theory because I'm not allowed to just boost my states wherever I want, or boost my particles however I want.
So is rotation, right? Rotation is not also a symmetry.
So in full rotation, so I still allow for like this combined rotation. So like, so for instance, rotation will change the dipole moment, but both the rotation of the entire space is still a symmetry of my theory. Okay, you can also violate this. This is again like a special case in which I still have rotations, but for instance, an X-cube model rotation is not a symmetry. You can take a 4 moment, if you slightly rotate it, it's not going to stay the same. So rotations are not a symmetry of the X-cube model, but this is again like a simple toy model for me to get going. Okay, so yeah, I start with these 4. These 5 operators, and then I add to it, as I was just saying, the dipole moment operator. Dipole moments together they conserve. They are independent. So like if dipole moment conservation in one direction is independent from the other, it transforms as a vector. And more importantly, it does not commute with translations. This is the most important thing for us, is that as long as the state has some finite charge, then the dipole moment transformation will not commute with the translations in that direction. So this is the most important permutation relation that we have in mind. Not really going to use it all that much, but this is just to tell you that the particular setup I'm interested in, there is a very concrete symmetry algebra in the field theory that I'm interested in.
So what is the Z algebra that they have there?
I don't know if, I mean, it's called in the literature as a dipole algebra. I mean, yeah, I have not gone into any more detail. I have only checked that this does form an algebra. So, but you can, of course, go and like try to find which group it actually corresponds to. I have not done that.
Sorry, naive question, maybe, but you are always creating these dipolar excitations from the vacuum. So what does the state having a net charge mean here? I mean,
oh, so so it's like, of course, you will, I mean, so you will have a net charge if you take like a subsystem, for instance. So if you have like a state, I mean, you started with some vacuum you created and then you split the system into half and you only think of one of them. So that's will be one way. I mean, this is like exactly like saying that in an ordinary fluid, I mean, you can only create positons and electrons together, but what does it mean for something to have a finite density?
So something local.
Yeah, so it's precisely like you take away all the electrons and then you are left with an ion. Right, okay, of course, corresponding to every operator, there is a conservation equation, the molecular identities. So of course, Hamiltonian leads to energy conservation, momenta leads to momentum conservation, translation to momentum conservation, Q leads to charge conservation. This is also very familiar. Ji is the angular momentum operator, which tells you that the Tij, the stress tensor, is symmetric. And what that ends up saying is that the angular momentum is conserved. Now, this is not really, I mean, I'm assuming here that there are no internal spin quantum number associated with my fields. Of course, then this is not enough. I have to also introduce a spin operator, but yeah, normally this is what suffices. And then I have this new symmetry where the dipole conservation implies that the flux is given by gradient of a symmetric 2 form. And this tells you that the dipole moment is conserved. So what we saw in the previous slide.
Do you know what is the center of this algebra? Does it have Casimir operators?
So I know that Q acts as a central extension in this algebra. So you can remove Q, and if that is the center or not, I cannot. Again, I have not studied in any detail the group theory side of this. I mean, what was sufficient for me, at least at the moment, was that it's a consistent algebra.
So now when you write this local conservation equation for your dipole charge,
yes,
you've thrown away these large extended dipoles we were just talking about, where you had a positive charge at some macroscopic distance from a negative charge. So that's another assumption you're making there. That all these dipoles are.
I mean, so this is a local conservation equation, of course. So
right, but
so I'm not really integrating over anything right now. So
right. But that then ignores these large dipoles we were just talking about, because now all your dipole moments conserve locally.
Yes.
Whereas before we just had an example where
they
conserve globally. You know, there's some big dipole.
Yes.
But they're skewed. The fact that they're skewed means that what you're saying cannot be right. Otherwise, the Q would always be zero.
Q would always be zero.
Yes, if the dipole wall is very small, then the net charge would always be zero, right? So that computation relation, I think if you cut the system across the dipole, then people will not communicate because they're just moving half until you change D.
Right, so we're throwing away these large.
I don't think if Q is not zero, then.
Oh, you are
not
saying we're keeping.
Yeah, you have some configuration with two charges like this, and now you cut the system here, and you only wiggle it here.
Yes.
And you pick up that Q term, which is the charge contained on the subsystem that you cut.
Okay.
All right.
Thank you.
Okay, well, thank you very much for answering that for me. Anyway, okay, so now I am ready to give you a concrete model. This was due to Pretko in 2018. So this is like a particular scalar field theory. This is not the unique field theory that you can write down for a scalar with these symmetries. This is just a prototypical example. And the important thing about this is that you of course can have any number of time derivatives because the Hamiltonian computes with dipole moment, at least in flat space, but it does not commute with momenta. So the first non-trivial term that you can have with spatial derivatives in such an action will be fourth order derivatives. So as you can imagine, so if you were to write down a dispersion relations for such a model, you will not get omega goes as k square. In this particular model, you will get omega goes as k to the power 4. So you will, so this is like, again, another salient feature of these theories is that you don't have a usual kinetic term. You have this derivative suppressed kinetic term. Other than that, you can actually go back and check that this particular combination works. So this combination has been engineered very specifically for it to be invariant in the dipoles. I mean, it's quite easy to see. It's like a small computation I did on the right. If you take this complex scalar phi and like split it into the modulus and the phase, then this term here splits into this term here. And the first term is, of course, transforms covariantly under both of these transformations. So first one is the local, normal U1 transformation, and the second one is known as the dipole transformation, which is like linearly varying shifts of the phase. And since this thing only depends on two derivatives of phi, so both of these are independent to symmetry. This also gives you a flavor of why they are related to subsystem symmetries, in the sense that phi is a complex scalar, and I'm allowing the phase of the complex scalar to not only change globally, which will be a symmetry of course, but I'm also allowing it to change linearly. So if you imagine any constant x plane in your theory like yz planes, then you can independently change the spins or independently change the phase of the entire field configuration in that plane. And this is a very large symmetry, as you can say. It's a pseudo-local symmetry. So it's not really local because psi cannot be an arbitrary function of x. But it's a pseudo-local symmetry because the space can depend linearly on x. So this is again a smooth thing of these Fractonic systems is that they have these pseudo-local symmetries. So they're not quite global, they're not quite local either. Okay, and you can take this, you can go back and do the Noether procedure. You will find all the currents, and they will satisfy the whole identity that I just told you. In particular, the flux will be given by the divergence of a symmetric two form. Okay, how am I doing on time? Not very well.
It's okay.
Yeah?
We should wrap up, including questions at 4:15.
Yeah, I'll try to not overreach myself. So anyway, so now what I'm interested in is that I want to gauge these theories. So if I wanted to gauge these theories, so this is what the premise of my talk is. I want to couple these theories to background spacetimes. So in this particular case, for instance, you can gauge both the U1 and the U1 dipole by introducing two copies of gauge fields. The first two are very familiar. Apart from the psi transformation, this is just a normal U1 gauge field which transforms with d of lambda. But then I have this additional gauge field, Aij, which is symmetric two form, and it transforms with the symmetric derivative of some dipole symmetry parameter, and Ai shifts under the dipole symmetry parameter.
So what are your conditions on lambda and psi, I guess? You have conditions on them, right? Because otherwise lambda would include psi.
Yes, so lambda can in principle be time dependent. Yes.
So
so now what I'm trying to do is I had these original symmetries, which were of course global symmetries, psi and lambda were constant. I'm trying to promote them into gauge symmetries.
local in time only, or
local in time as well.
okay.
So now lambda and psi will both depend on space and time. Yeah, so
Can you go back?
Yes.
If lambda is local in space, why doesn't it include the psi I, xi?
Oh no, I'm saying that here at this level, of course, this is a global symmetry. Now I'm trying to gauge this. So I'm trying to
But the guy is saying once you make it local, how do you distinguish lambda from the other one? Because
oh yes, so you won't. So then the dipole transformation will really only act through this guy here. So once you have gauged, this is almost like translations and rotations, for instance. So once you promote translations into local symmetries, there's no way to distinguish them from rotations. It's like almost the same kind of picture happening here. Then the dipole transformation will only really act through the gauge field.
So that lambda goes to constant.
Yes. But psi will go to like 0.
So very important.
Psi will also go to a constant, I imagine, no?
Oh yes, there is a global symmetry, so yeah, you don't need, so psi can also go to constant because, yeah. Anyway, so what is, I mean, I think this actually doesn't really appear in the psi language, so maybe if it's more clear to you, you can gauge fix A exactly to 0 by treating, by treating psi equals to minus grad lambda, and then you only need to introduce a time component gauge field and a symmetric two component. So in that sense, there's only one U1 parameter lambda, and this is like a larger symmetry. Now, of course, then you only have one local parameter. Maybe the same. But okay, once you have introduced these gauge fields, you can gauge the original scalar theory you had. So the normal time derivatives becomes covariant time derivatives, as we have it. You also have covariant spatial derivatives. And my previous definition for this non-local covariant derivative between two copies of phi fields actually changes to this operator here. And not going to do that, but it's actually quite easy to go back and check that this action is invariant, this symmetry is coupled to the symmetry that I had on phi fields. And of course, the most utility for me, at least in coupling these field theories to these gauge fields, is that now you can start probing these systems by treating these gauge fields as background fields. You can start to really probe JD, JI, JIJ, and you can obtain them by varying the action, or in the field theoretic description by varying the partition function with respect to these gauge fields.
Can you say more about why the scalar field theory is a good starting point? You said explicitly it's not it's not the most generic action.
Yes, right now it's a toy model. You can also write other kind of theories. I'm not sure if people have written down fermions as such. We will have written down other kind of theories. There's the vector charge models, scalar charge models. There's the other models, but I'm just using it as a toy example to try and motivate how to gauge systems with these kind of things.
Could you do a renormalization group analysis of what your good starting point
all the symmetry you are talking about is survive when you quantize the theory, and the partition function will be invariant.
So I think people claim that the scalar field theory that is written here is not anomalous, but it's I don't know whether any. Of course, I don't know whether. So there is a lot of discussion in the literature. A couple of papers, at least I know, which talk about anomalies or anomaly influences, things like that. So you can, in principle, you can get anomalous systems. Now, whether or not the scalar charge theory that I'm talking about is anomalous or not, I don't know. Or probably it's not. I don't think people have done the full loop calculation, but there are anomalies. So you can have setups where this dipole shift symmetry is anomalous. So they are like mixed anomalies between U1 monopole and U1 dipole. Okay. So now I want to, this is just the normal thing. And now I also want to write down some gauge terms if I want to make these background fields dynamical. It's quite easy to see that the usual monopole field string, by the way, now I've switched to some new indices, which will also include time and space. That's a covariant notation. Although I do emphasize there is no Lorentz symmetry, so the system is not relativistic, it's just a notation. And if you define F mu like that, you can quite easily see that neither electric or magnetic fields are invariant under the dipole symmetry. So the usual Maxwell's kind of term that you would write is not allowed. And it's also easy to motivate it physically. Of course, if you were to apply an electric field to a dipole, then it will move plus and minus charges opposite to each other and will violate the dipole transformation. So
previously the gauge field was either Aij, right? Now it became A mu, or did you not use?
Oh no, so this I'm just talking about the usual electromagnetism here. So I have an AT and AI. I'm just saying that the usual electromagnetic gauge fields will not exist. I wouldn't be talking about these gauge fields if there was not a consistent description of the matrix at this stage. But okay. Then there is, however, there is this composite object that you can create. So for instance, F I know is invariant under U1 monopole. It's not invariant under dipole, as is occurring here. But I can then use the Aij symmetric field to create these combinations. You can look, this is some algebra to figure out, but at the end of the day, you can define this composite object. It is actually made out of these two objects here, and it transforms almost like a gauge field for the side. And once you have obtained a gauge field that looks like that, then you know very easily how to write down theories that are invariant under this. Of course, you define an FMU object like that, and this will really be invariant under the backward shift symmetry. So now I told you almost everything that you need to know to create an action, for instance. So you take FK mu and you just split it into components if you want, or you can also stick to covariant notation if you want. But there are an electric field. So this is like a version of electric field, but for dipole symmetries. And then there is a version of magnetic fields. And once you have them, you can write down this gauge term, for instance, this given here. And this term is explicitly invariant under U1 monopole and U1 dipole symmetries. A lot has been done. For instance, in this 2016 paper by Pretko, like people have taken this theory and did all sort of electromagnetism mumbo jumbo with this. You can go ahead, but I think the only thing that really I should want to point out is this here that you have a well-defined Maxwell's sort of equation.
The ghost decouple.
Yeah, so this is only at the classical level. I don't know if people have quantized.
No, going to talking about classical ghosts, like the negative kinetic term.
It's on an issue.
Okay,
Yeah.
That's sensible. Yeah, basically as long as
it's a free theory, right? It's just a quadratic.
Yeah.
Then how many degrees of freedom does it have? It's about the same question.
Typically, I would expect that you can gauge fix the dipole symmetry entirely by getting rid of AI. So then you only have an EIJ symmetric tensor and AT. And AT you can remove by gauge fixing lambda. So most probably it's symmetric tensor gauge. It only has degrees of freedom of a spatial rank 2 tensor symmetry. Anyway, so now I think after long last I have arrived at what I really wanted to do, but I think it's good because a lot of this was going forward is quite technical, so I can just gloss over it for the most part. But what I want to really do is couple these theories to curved space-time background. The motivation for doing that are manifold, but my primary motivation is that so that you can consistently define conserved currents in these theories, which has not been done so far, because you can define them by taking variations with respect to the equivalent of the space-time metric in your relativistic theory. Also, like having Fracton systems on non-trivial space-time backgrounds or curved space-time backgrounds has also gained a lot of attention recently. But I think the most peculiar feature about these theories is again because there is no boost symmetry, neither Galilean or Lorentzian. So you cannot just couple it to any given space-time. Particularly the space-time that you couple it to need to have a preferred sense of observer or reference frame because there is no boost symmetry. And that's like the most technical part of trying to couple these systems to curved space-time. And these are like the so-called Aristotelian backgrounds that came a couple of years ago. So it's a fancy name for a space-time background that depends on the frame of reference.
You have rotation symmetry in special directions?
Yes, so I still have rotation symmetry because of the theory that I'm considering, but in general, you could also like let go of that. But right now, I have rotation symmetry that just don't have those. Okay, so this is like Aristotelian spacetimes in one slide. I think the most non-technically speaking, these spacetimes have a version of spatial metric. For instance, this is Hij, which is completely fine. And then they have a version of time metric, which is equivalent to GTT and GTI. There's NT and NI in this notation. But they also have a preferred frame observer, VI, of course. And that was the whole idea that these are Aristotelian backgrounds. They come equipped with a preferred reference frame. So that's the V. So this forms like the metric with observer set. And then, of course, if you have some U1 conservation, then you have the normal U1 gauge fields.
Is it related to Newton-Cartan geometry?
Yes, so it's the Newton-Cartan geometry. Typically, you also impose a minimal boost symmetry which so you introduce these, but you also introduce a boost symmetry, which the Galilean boost symmetry which gets rid of the BI there. So it's let's say, I mean, I think for all practical purposes it is the same, but the word Aristotelian really means that there is no boost. Anyway, so you can covariantize all of these objects, and essentially these degrees of freedom or these independent fields that are listed here are equivalent to all the fields that I've put there, and they are the typical building blocks of Aristotelian, or as I was mentioned, Newton-Cartan geometries. You have a flock form nu, you have a frame vector v mu, you have spatial metric and cometric, which importantly are not inverses of each other, because h mu nu by itself is degenerate. It has a zero eigenvalue, so it cannot be inverted. Then have the usual mu gauge field, and the objects in the first two have these sort of completeness relations, which essentially tell you that at the end of the day, the independent degrees of freedom are just here, right here. And the flat limit is defined as nt is 1, hij is Kronecker delta, and everything else, which is the usual kind of thing. This wouldn't be a lot of a geometry if you couldn't define a connection. You can define a connection. This is not a unique connection, unfortunately, unlike relativistic theories, but this is some connection that you can work with. And this has the property that it annihilates some components of the metric, doesn't inherit others. There's a lot of discussion on Aristotelian and Newton-Cartan connections in the literature. I don't really need to get into all of that. What I'm interested really is that once I've defined these fields, I can, so these are like background fields, and then the space-time symmetries can really be thought of as some local symmetries acting on the background fields. So if you have a partition function that is given in terms of some background fields, which you can use to compute some operators, then any space-time symmetry can be thought of as a local action on these background fields. So as it turns out, infinitesimally speaking, the space-time translations act as a diffeomorphism on all the fields. This Lie x denotes a Lie derivative along chi mu. It's a little technical here, but unfortunately I can't avoid it. And A, in addition to the Lie derivative, also has a gauge transformation piece. A lot of technicality aside, at the end of the day, if you were to take like a partition function and you define by varying it these conserved currents like that, so you have you have the charge current, energy current, momentum density, energy momentum tensor, or stress tensor, some constraints here, then you can eventually find some conservation equation. This is like the usual kind of thing you can find in all of these papers below. So the idea is that this is like a consistent set of setup, and you end up getting an energy conservation in curved space, momentum conservation, and a charge conservation. If this looks pretty weird to you, in the flat limit that I had just mentioned, these just turn out to be the usual things that you would expect them to be.
Well, all of them are classical source here.
Oh yes, they are classical sources. Okay, just a little aside. I don't know if I have time for asides, but I think it is important.
I need to wrap up in the next 10 minutes.
Okay.
So if you want to have time for a couple of questions.
Yeah, okay, let's do that. So, I mean, just an aside that if you want to take special cases, if you want to couple these systems to boost symmetries, which is not really relevant here, then the Galilean invariant systems, you can do that. It turns out that infinitesimal Galilean boosts act like this, and at the end of the day, they tell you that momentum density is aligned with the flux, and okay, the end is not working. Oh, there you go. Similarly, there is a discussion about Lorentz boosts as well, which correspondingly sets the momentum density to the energy flux, and that's the same kind of idea. Anyway, so this is the most important bit, I think, here, and then I can start wrapping up, is that you have to introduce, if you want to describe systems with conserved dipole moment, you have to also introduce another source that is coupled to Jij, which I will call this A mu. I think I've mixed up notations. This is supposed to be a small a here, and it's really telling you that small a is symmetric and it is purely spatial. And again, what you do is like you introduce this a, the diffeomorphisms act on it as you would expect. But in addition, there is this real piece here, which is a covariant version of the Aij.
Small a is the Aij that you have been
yes, yeah. So this is supposed to be small a.
But that's a form, right? How can it be symmetric?
Oh, so I was calling it symmetric 2 form for So it's a symmetric two form because it couples to Gij, which is symmetric.
Yeah.
Sorry?
Maybe you should call it a form.
I mean, it's like, yeah, I mean, I think it's in the same way you call metric a bilinear symmetry bilinear. So yeah, but yeah, yeah, okay. It's not a differential form. It's just a symmetric matrix. If you quadratic. It's a quadratic. Anyway, so
there's no field strength associated with that because that's.
Sorry?
There's no field strength associated with this little aij.
No, not right. I mean, there is this big object.
Let him finish. Because we got
Okay, sorry.
Let's keep questions for when Akash has finished.
Thank you. So yeah, so these are things like that, and then you can of course define this JB operator, which is the covariant version of this Jij operator I had before, and so essentially the same equations that I had before follow again, but in addition, I get this equation here, which I was after, is that the gradient of this, or the flux, the charge flux is equal to gradient of something. So these are like the covariant generalizations of everything that I was talking about so far. And here at the end of the day, now once you have computed the conserved currents, this is also something important, is that now you can start asking questions. How do they transform? Now we know that all of these operators are U1 invariant. So we all know that energy, momentum, everything is gauge invariant. We also know exactly how they transform under space-time translations. They will transform as like diffeomorphisms. But in particular, none of these quantities are actually dipole invariant. So they will all transform under dipole shapes. And this is a lot of notation, but at least you can again look at this in the flat space. In flat space, I'm just telling you that energy density and energy flux happens to be invariant, and it makes sense because energy is associated with time translations, which has nothing to do with dipole moment conservation. But momentum and stress are not dipole invariant. So for instance, if you had like a momentum, and of course, if you apply dipole shift, the momentum does not commute with dipole shift, so the momentum density will correspondingly not be dipole invariant. And the same goes for tau J. So this is like something important is that if you were to find momentum density or fluxes for or stress tenses for these theories, they will not be covariant objects. This is almost same like having in Galilean theories, or I mean, for instance, momentum is not generally frame invariant. So it's the same kind of object. Anyway, this is something which I can skip. These are just telling you that how to couple these theories, and at the end of the day it works out. That's what I'm trying to say about this. One important thing that I do want to mention is that what happens when you try to covariant the gauge field theory. So before I had these gauge field strengths, I had defined this AT, this composite object, which transformed as a gauge field under dipole transformations, and I use this knowledge to compute an action for this theory. As it turns out, it doesn't quite work on curved space. Is that on curved space, the natural object to define, which is the covariant version of this, I have given on the left, and it has a very complicated transformation under dipole shape symmetry. So it does not transform anyway as nicely as this, and this has very real consequences. Is that the covariant object that you would define like this is no longer invariant in curved space. So in other words, the symmetric tensor gauge theory or these electromagnetic fields that couple to dipole moments are actually not covariant on curved space. You can sort of imagine that there will be problems with dipole shift symmetry anyway on curved space because charged particles moving in a curved manifold might not typically have their distances conserved as they move through space, or if the space is changing with time. And this is reflected in this. But what it really means is that if you were to take this theory and directly try to covariantize it, you will not get a dipole invariant description. In other words, there is an obstruction to couple the symmetric tensor gauge theory to curved space, or in other words, I mean, if you want to think of it like an anomaly, I'm not sure if it is, but this is really just saying that you cannot gauge diffeomorphisms and dipole symmetries together. You can do something similar, is that a free dipole symmetric tensor gauge theory cannot be coupled to space-time, but if you couple it to some scalar, in for instance, I had previously phi, and you can define this composite object, which is dipole invariant. And this is a very complicated term. It's not a quadratic theory anymore. So you can ask questions whether it's a nice theory or not. I have no answer to that question. But what does seem to happen is that if you take this theory and now go to the Higgs space, where phi condenses, then this will give rise to some sort of local theory, some sort of local version of the symmetric tensor gauge theory, plus a lot of interactions. But the important thing to note is that you cannot do this for a free theory. You can only do this for. Anyway, so that's where I wrap up. The continuum. So what I've really talked about is that the continuum description of lattice models with fractonic degrees of freedom have this exotic dipole and multiple symmetries. In this talk, I only fixated on dipole symmetries, but you can also have multiple symmetries. And we learned how to couple these theories, such theories, to curved spacetime. The talk again, I only focus on dipole, but in the paper that I had cited before, you worked out the multiple symmetries as well, how to gauge them. And an important feature that I noted was that there is no boost symmetry, so you can only really do coupling to Aristotelian spacetimes, not relativistic or Newton-Garton spacetimes for that matter. And an important fact that I want to note here is that the symmetric tensor gauge theory cannot be coupled to general curved spacetime. I'll leave you with a little of these. Is that there is a question whether there is whether the obstruction to gauging the free theory can be thought of as some sort of anomaly, the dipole gravitational anomaly. I don't know whether there is an anomaly info mechanism that you can really work about here. There's clearly an obstruction. Whether that obstruction can be thought of as an anomaly or not, I don't know. Then I really work a lot on hydrodynamics. So my motivation for doing most of this is to try and work out some hydrodynamic description at low energies, which will apply to these fractonic systems. And as it turns out, what identities or conservation equations and how the various constitutive relations transform in the various symmetries is pivotal in doing anything. So that's I take this as like a groundwork for further explorations in that direction. And there was, I think, some question along this direction. I'm not sure, but just like whenever you have spin conservation, you can also talk about internal spin. So you can have particles that have some internal spin density associated with them, and then Tij is no longer symmetric, but the antisymmetric part of it is given by some conservation of spin, local spin current. And there's like a similar story you can work out here, is that if you have fundamental excitations that have a fundamental dipole associated with them, probably a question before, I don't know, but then you can also try to generalize these theories to degrees of freedom that carry an intrinsic dipole moment. But okay, that's where I leave. I had some slides on fluids, but let's just put them if someone is interested later. Thank you, and it was really nice to talk to you guys, and I hope you found it a little bit insightful. Thank you.
We have time for a few questions. Then there's a coffee break that awaits us on the second floor.
Do you take it?
Yes.
So when you try to write down a relativistic fluid dynamic theory for this, then
you cannot, because relativistic has Lorentz boost invariance, so you would not be able to write down relativistic or Galilean. But you can write down like these boost agnostic hydrodynamic theories that people have been talking about recently. You can at least try to. There is a lot of obstruction in trying to do that, precisely because momentum does not transform covariantly. So, for instance, you can imagine you cannot really define a thermal state all that well, because if the thermal state has finite density, then it cannot move. So it doesn't really make sense to talk about fluids here, because this state cannot move. And if it can move, then it cannot have finite density. So there is like a lot of problems in trying to, how would you even go about defining a thermal state with these systems? So I mean, there has been some work, but I think a lot has still to be worked out in terms of how sensible these fields will be.
How do you know that this object that you define in curve space is the unique one that you could define? This combination of gauge fields.
I would not know that. So of course, I mean, you can, of course, I mean, so covariant generalizations are modulo adding terms that would vanish in curved space. But at least, I mean, for the quantity of interest, when I was trying to define the symmetric tensor gauge theory to curved space, I could not find, or at least I don't think there exists a curve space generalization which would make this theory invariant. But that's, of course, is up for debate as well. Is that, of course, whenever you covariantly generalize an object, there is no such thing as unique covariant generalization, because you can always take anything and then you just change it with curvature terms that would otherwise vanish. Yeah.
Could you comment on the status of the de-Brownianization of this type of theories? If they exist, they should answer the question about coupling to curve space.
I don't know. I mean, there has been some work on trying to couple it to curve space before. What people have found is that symmetric tensor case theory can be coupled.
No, I'm asking about the embedding this.
Yeah, I do.
Can I ask about the scalar field theory you were talking about?
Yes.
Maybe you want to pull up a slide, I don't know. But how seriously should I take this as a theory, an effective theory describing fractons? Because it has some rather, I mean, before having all the gauge fields and this, because it has some rather weird properties, right?
I mean, okay, so this field theory can be thought of, okay, I think it takes some time to get there. It is still working on it. Okay, so so in the sense that this field theory has some fractonic features. Now, this theory itself does not describe, for instance, the X-cube model. So X-cube model has further restraints that a dipole can only move in certain things, and people have some idea of actually, even like the original papers on this theory, they have, I think, a very good idea of how do you have to modify this theory to define the X-cube model and describe the X-cube model in the IR. Yeah. So, but this particular theory is supposed to be just a one model. So, but I think people have taken other variations of this theory, where basically you violate rotational symmetry and you only allow for some space derivatives to occur in some combinations, so that there is an cube rotation symmetry, but not a full rotation symmetry. So if you break the full rotation symmetry down to its cubic subgroup, then that theory does seem to describe the large distance behavior of quite well.
But you're not going to change the fact that your kinetic terms.
Oh no, that's not. Because the thing is, this is the minimal symmetry. Then on top of it, you need more symmetry. So dipoles are anyway conserved, but then dipoles are further restricted. So some components of the quadrupole are also conserved. So so this in the sense is the minimal symmetry that you need. But then on top of it, you can also impose other symmetries.
So when you learn,
let's take a final question online, and then we can continue discussion during the break for the people in the room. Alexander, can you ask your question?
Yes, thank you. So this action right here, it's actually not the lowest order action that you can write, because you can write order 2, but it will just be a longitudinal term. So if you want transverse, then
yeah. So I did point it out in the beginning. This is not the most general term that you can write down. So there are other terms, and people have done a lot of generalizations with this. But yes, you're right. This is not the most general term that you can write.
And also I think you mentioned before that basically for a theory to conserve dipole, you want the charge current to be written as a total divergence.
Yes.
And mathematically, this can always be done, because given any vector, I can always find a rank 2 tensor, actually an infinite number of rank 2 tensors that I can take divergence, and it will give me back this vector. So it seems to me like it can always be done.
But it is more of a question of whether you can do it globally, right? Locally you can do it, but whether you can define such an object globally is the real question. It's of course true that you can take any vector and you can split it into some divergences and some curves, but whether you can do it globally or not is really the question, whether these dipole moments are conserved globally or not.
Oh yeah, okay, thank you. Yeah, that's a good point. Also, sorry, just one more question, because I've noticed that you were using the gauge field, which was a temporal part, spatial part, and then the rank 2 tensor part.
Yes.
And actually, what is surprising to me is that you are actually using the vector gauge field as well, because
this is just to have some sort of covariance in my mind, really. As I just mentioned on the slide itself, that you can gauge fix AI to 0 by choosing your dipole shift symmetry in a particular way.
Okay, so basically this vector gauge field is pretty much not there.
Yeah, it's just not there. It's a good characterization of what we want to do after. But of course, you can always go to a gauge where AI is 0, and that is completely fine.
Okay, thank you.
All right, let's thank Akash again. And,
That's right. Yeah. With the first break since